Thanks a lot, Mark, for the introduction, and thanks a lot, Yuxi, for the invitation. Hello, everyone. So today my talk is named Building the Cognitive Engine for Foundation Agents, which is slightly different from on the web page, but it's the same content. So maybe the most basic question, what exactly is an agent, right? If you check the textbook from the Berkeley, it says that an agent is anything that can be viewed as perceiving its environment and acting upon that environment through actuators. So you check this framework, you see there's an environment, you can get the perceptive signals from outside, and through a cognitive process, you make decisions about actions, and then it will be executed by actuators. What's in that base? What's the cognitive part? So how we can define it, what's the structure, and what are different components we have there? So that is what we care about. And if you check this figure, it's from the Dr. Wen Lian's blog, which shows from an LLM, how you build a very basic and elegant agent. So basically augmented with some modules, like memory, tools, planning, action capabilities, and so on. So basically, from traditional agents, which is like rule-based or machine learning, statistical model-based, and so on, more specific, domain-specific, and now we have LLMs. So it empowers agent with natural language fluency, strong reasoning capabilities, and adaptability to different domains and tasks. But like we can see, the capability, the efficiency, and so on, they are quite very good right now, although we can still keep improving it, but there are also key limitations. For example, the safety, trustworthiness. We can still improve its multimodality, which is not as good as pure text, empathy, emotional support, embodiment, and so on. So we want to know, where are we now in the landscape of AI research today? There are so many topics, so many exciting research out every day. And we also want to know what can be improved through which paths. So we want to come up with a unified framework for AI agents. We want to improve the lifelong learning, complex reasoning capabilities, emotion grounding, multimodality, and so on. So like this is one of our recent like large-scale survey paper. We collaborated with 20 institutes from the globe and more than 40 others. So it is available on arXiv, which covers a much more comprehensive content than what I can cover today. And we're releasing a new version by the end of this month. So you can check this paper for more details. But today, let me show you like the core ideas here. So our main idea is that we want to connect AI with human brains. So we're not saying that, okay, human brain is the best, and we should replicate every characteristic we have. Instead, we want to have a critical comparison between biological intelligence and machine intelligence. So in this case, like, we want to draw insights from both sides and know what can be improved, what can be better, right? So let's say if you consider different capabilities, let's grossly categorize them into 3 levels. Let's say L1 means, okay, this capability is well developed, like the language understanding and generation capability, which is quite strong for large language models. The visual perception capability from computer vision communities. So these are kind of well developed, and you can actually bring great value for the real applications. But there are also many capabilities which is like have been researched, but we still have space to improve, like the reasoning, the different type of memories, and so on. And also some are less for example, the tactile perception, the emotional support, the global workspace, and so on. And also we can see there's so many different topics, right? So let's say people are talking about learning, planning, reasoning, the workflow, the MCP agent-to-agent protocols, tools, like skills, and so on, world models. So I would say current AI agents, many of them are built in an ad hoc style. They don't have a quite comprehensive framework, and like simulate integration of different paths. And human brain is more integrated yet modular approach served as inspiration. So we want to come up with a more well-defined framework. And these are some symbols we defined for it, but we don't need to remember that. So let's check this figure. So from a high level, you can see it's similar. Like we perceive the world, we get observation signals, we make decisions, and then we have some actors to execute your action. But what's defined is more the internal side. How does the cognitive process work? So if you consider, we define several different types of mental states. So I would say mental states are the critical components inside the cognitive part. So like world model to predicting the future, memory to store experience and retrieve information, and reward, emotion, goal, and so on, to motivate the agents and so on. So basically, based on it, we define the cognitive process. So let's say if you have these mental states, we consider what is cognition. Cognition is composed of learning and reasoning. So when we say learning, we mean that it's kind of a long-term update about yourself, right? And those mental states define the critical parts of the agent itself. So which we have this learning function, the mental state m of t is equals to a learn function given the last time step mt minus 1, your last action at minus 1, and your new observation O of t, which means you're updating yourself based on your past experience, right? And based on the updated mental state, you're reasoning about the current context. So we define the reasoning as making decision about the action A of t, given this m of t. So this learning function L and reasoning function R compose the whole cognition process C. And then, no matter what kind of actions you have decided to take, you need to execute it to impact the real world. So we still need an actor to execute these actions. So for example, let's say when you do robots, is such kind of continuous control is kind of more challenging than just execute and command in the digital world. That's why like different actions will have different difficulty level, so in different environments and tasks. So through all of this, we kind of define a framework to combine the perception, cognition, and action. So what we wanted to be able to do, so we define what we call the concept of foundation agents. We call it foundation is because that we hope that it can be generalized to different types of tasks, different environments. And we emphasize on its capability to form a multi-agent system because we think even if you can build, let's say, a super powerful single agent, it may be not the most suitable, most effective and efficient way to solve complex tasks. So a foundation agent should have general cognitive perception and action capability, which enables them to kind of complete tasks in any kind of environments. And also, they can be collaborative, work together to form a comprehensive like multi-agent system, which reflects the human society structure. Right? I don't have enough time to cover all the details of the long survey paper, but I would like to share two of our recent research. One is about memory design, and another is about the reasoning capability, which are the core two pillars of the cognitive process. So the first work I want to share is called the R3-MEM architecture. So this paper is also available on arXiv. It's adopted by ACL this year. So it's called Bridging Memory Retention and Retrieval via Reversible Compression. So you can check it on arXiv online. Let me show you the core ideas here. So first, LLMs are stateless, right? So let's say whenever you give an input to the LLM, it gives you an output. But actually, next time, if you give it a new input, it doesn't have memory about your last conversation. If you think about ChatGPT, like the thing how it works is like every time you input a new like text, it will concatenate it with the historical information. So actually, for each single pass is stateless. The past experience is not retained. So usually, people will connect an LLM with some kind of storage. We call it memory. So attachable memory buffers evolving over time. So it enables continuous dialogue, personalized agents, and long horizon tasks. So how memory is defined? So usually you have like two typical ways. One is some kind of explicit storage. So let's say you store every dialogue we have had between a user and an agent, either in textual manner or in a vector database, a relational, a graph database, or KVCache and so on. So this is some like data format you stored explicitly. Or you can like keep learning through this conversation, through this memory, and store it in a parametric way, like a neural network, right? So it's kind of implicit memory because the information is stored in ways. So there are pros and cons. So for explicit storage, like it's easily editable, it's interpretable, you can store every raw bit of information, right? But also there's extra latency and storage cost. With more and more information stored, it's hard to scale up. You will need more time to conduct accurate retrieval. And for implicit, the internal way, so it's easier to scale up because it's stored in the weight, right? You're just adjusting the weight. You don't need to scale up the scale of the database. So it's always available. The latency is lower than explicit storage, but it's also harder to update. You need to edit the implicit knowledge. It's hard to probe and edit. It's harder to control. And maybe you cannot memorize every accurate details. Maybe we have produced some hallucination, right? So in our work, we want to, what we say, bridging the gap between retention and retrieval. So for retention, which means that we want to retain the accurate information as much as possible. So, and for retrieval, it's like we want to make the retrieval efficiency fast. So as we said that if you compare the explicit and implicit memory, they have the trade-off, right? Either you can retain the accurate information, but you will suffer from latency for the retrieval process, or you have a fast retrieval because it's just directly generated by the memory network, but maybe your retained information is not accurate. So we want to bridge this gap, try to maximize the trade-off. So how can we simultaneously maximize this retention and retrieval while keeping the external storage minimal? So basically, this work is more focused on the implicit memory network design. So if you consider it, like we have several key ideas. The first key idea is we consider memory as a compression process. So let's say retention is you have the original context. We compress it into a memory format. And for retrieval, it's like we want to decompress the memory and recover the original query context information. So this makes them naturally a dual task. So which leads us to, we need a reversible module which can give X, we get Y, and give Y, we can recover X. This is the research question of the reversible neural network, which is a research topic, and there are many works about it. So this is one quite classical work, where basically you define F and G, two different modules, and you define X and Y using this F and G function. And you can see from X, you can calculate Y, and from Y, you can calculate back of X by utilizing these formulations. And similarly, now if you have transformer, we can also turn a transformer into a reversible transformer by two adapters. One adapter represents F module, one adapter represents G module. This is from the prior work, the reference one. So this is our idea two. So idea one is we need a reversible neural network architecture. Idea two is we need to turn a pre-trained LLM into a reversible transformer. So why? Why we need to transform an existing LLM? Because it's we consider a memory network which is good in understanding the memory information should be at least good in understanding text itself, right? So in this case, we need a pre-trained language model instead of training from scratch. So let's say Llama model or any other open source model, they're not originally a reversible transformer. So you need to adapt it into a reversible transformer architecture by this adapter-based architecture, and you fine-tune this adapter so that you are conducting a perfect parameter-efficient fine-tuning, right? And last, we need to get the data. So what we have been doing is we take a pre-trained language model, we turn it into a reversible transformer module, and we want to fine-tune it so that it can be better to serve as a memory network. So how to get the continuous training data? So if you consider it, we say that it's kind of a compression and decompression. So you can take, let's say, long context, let's say long documents. You can compress it into different granularities from document length to paragraph level, paragraph to sentence level, sentence to entity level, which naturally mirrors the hierarchical structure of human language. And this can be done by taking a lot of high-quality documents and have an oracle language model, let's say ChatGPT, to compress it. And based on these different granularity context query pairs, you have such kind of data which can continue to pre-train your changed transformer model. So this is the final R3-MEM architecture. So you see, on the left is the data. We have different granularity pairs from document level to paragraph to sentence to keywords level. And on the right, we have the reversible transformer architecture, which is adapted from a pre-trained language model. We also designed what we call the memory token. So what is a memory token? So let's say when you compress a long context into a short query, and when you compress it further into a shorter one, you need to have some implicit token to memorize the whole context, right? This compressed token is what we call the memory token. So by combining this automatic data construction, the reversible network architecture, and these memory tokens, we can continue to pre-train an open source model and turn it into a memory network. and we conducted different experiments. This is the loss, which is for the forward generation, like from query to document, and from document to query, so forward and backward, and the cycle loss, right? We want to maximize the consistency between the recovered context and the original context. So this is the loss design. And we have achieved a good performance. So the model sets new sorter across different data sets, and it also performs well in both in-domain setting and out-of-domain setting. And we can see generally out-of-domain setting is not as good as in-domain, which is general for different baselines and our method. And we also, we plug in this RCMM model into an existing agent framework, and we compare it, how it performs compared to existing other memory design, like memory bank, memory reg, and so on. And we show that in terms of different metric dimension, RCMM works better. So this is some ablation study to see both the data pair construction, a virtual memory token, and the backward path, the cycle loss and the reversible design. Those are critical to the performance. So this is the first work. So to summarize, we frame memory as a reversible compression problem in this RCMM. And RCMM is an adapter-based reversible transformer with virtual tokens. And we achieved a sort of performance in terms of memory retention and retrieval, as well as good performance by plugging it into downstream agent framework. And you can see this is a general memory design. You can actually, if you have your own agent framework, you can plug in this memory into your own system, right? So this is about memory. The next is about the reasoning capability. So how LLMs adaptively combine fast heuristic and deep reasoning. So what is this? So first, this work is called System 1.5, like reasoning traversal in language and latent space with dynamic shortcut. So which is also available on archive. So we call it System 1.5. You can imagine that it's something trying to bridge the gap between System 1 and System 2, right? So we say System 1 is like more fast, intuitive way to make decisions, and System 2 is like slower, more deliberative way to think things carefully, make decisions carefully, which takes longer time, but can solve harder tasks. So first, what is the challenge for the existing reasoning methods? For example, chain of thought, right? It's quite intuitive. Let's self-task one step by another. So although it improves the reasoning performance, but it's often inefficient. So there are many steps which don't actually contribute to solve the task, and the model often overthink. So let's show an example. So this is, you input a query to, I think this is one of the sort of open source model, the QWQ, 32 billion. So you ask, what is 2 plus 3? If, like most of us will just respond, is 5. But the model will think a lot. So, okay, 2 plus 3, that's a pretty straightforward arithmetic problem. I think I can handle this, blah, blah, blah. So he also, it also output 5 different solutions. And finally, it put up all of this together. Okay, I'm quite confident 2 plus 3 is 5. You can see for this very simple question, it utilized 901 tokens, which is a huge waste, right? So, prior research to solve such kind of challenge, there are 2 different ways, either improve the language level efficiency or latent space reasoning. So what is the language level efficiency improve? So basically the idea is that either you produce less tokens to reduce the token count, or you reduce the computing of each token, so to reduce the overall cost. But the drawback is that you still decode every token for the fluency, regardless of whether it helps reasoning, right? And another way is bypass the language constraints. Let's do the reasoning in the latent space. So the core idea is that we can skip some intermediate language decoding, and we can have compressed, fast latent reasoning. We can also extend some slow latent reasoning by inject some special tokens, to indicate the pause or deeper source and so on. But the limitation is that by applying reasoning, they're still applying reasoning uniformly, which means it doesn't differentiate different cases. Sometimes we need to make very easy and fast intuitive decisions. Sometimes we need to think harder because this reasoning challenge is higher at some critical steps. But those works doesn't differentiate such kind of steps. So this figure intuitively shows how they work. If you think about chain of thought, right? It's like at each step, you output each token. So those tokens are like reasoning tokens before you get the final answer. So it's like the process of solving these tasks. And there's some early exit. So maybe the color is not obvious here, but you can see some white colored hidden means actually we can stop. Let's say if you have 20 layers transformer, but it's not always, you need to go through 20 layers. Sometimes you just need to go to 10 layers. That's good enough to infer what is the output token at this step. So in this case, this is called the early exit to reduce the reasoning depths. They also compress the latent reasoning. So it's like you don't need to output the final like reasoning tokens. You just continue the generation in the latent space and directly output the answer. And there are also extra latent reasoning, which you inject some special tokens. And our idea is that like we should be able to like traverse more flexible in the latent space. You can either go deeper, you can either have a quick skip shot, like shortcut, right? From this time t-1 to time t. So basically, like it bridges different ideas, it unifies different ways. So let's say sometimes you know the token quite early, so you don't need to go to very deep. You just infer for a few layers. Sometimes like this reasoning step is kind of easy. So you can directly jump from last t-1 step to the next level t, so which is a horizontal shortcut. So that's why we have two shortcuts. The depth shortcut, which reduces the vertical transformer depths, or the horizontal depths, which like have a fast reasoning. So how to do this? So basically it means that at each reasoning step, traditionally you just go through layer 1-1, L-1 to layer L. And after you go through every layer, you go to the next time step, you repeat this process. But now you can choose 3 different states. You either continue the depths, right? You need more depths to reasoning, or you can have a horizontal shortcut. Okay, I'm clear about this step. I can quickly go to the next step. Or you're clear about the answer already. So now you can exit and start to produce answer. So which means we need to have a gate. Well, this gate will decide at each time step, at each layer. Shall I early exit? I know the answer. Shall I continue infer? I need more reasoning. Or shall I go to the next time step? I can continue with fast reasoning, right? So how to get such a gate? There's some challenge. The challenge one is your original language model is trained with textual tokens, right? You don't have such kind of implicit label. And the second is, what are the key steps? What are the normal steps? So you need to differentiate fast reasoning steps and slow reasoning steps. And we solve this by, like, the first is we have the latent alignment. Let's say you have a reasoning model which is already fine-tuned with chain of thought reasoning. Let's say you have a good large teacher, and you can distill a student model by aligning the latent representation without output token. So basically, it's like, although I didn't output the intermediate tokens, I can align the hidden states. So this solves the challenge one. And the second is we need to have the label the tokens which paths are like fast reasoning, which paths are slow reasoning. So this can be done by relying on existing work, which is called autonomous thought, which can decompose the question answering data by into different pieces. Basically, it's like parsing the logical structure into different trees. And you can consider these roots of the trees are the starting of different reasoning pieces. They are critical steps. And the following steps are kind of easier because they are following the start. So in this case, you can label the data to be, okay, this is fast reasoning step, this is a slow reasoning step. So by combining this latent alignment and explicit data alignment, we got the data to learn such a model, which can mimic the latent space and also decide based on fast reasoning or slow reasoning. And this is the training objective. I will skip this. So let's check the accuracy. So this is the main experimental result. So the code is here. So if you check, you compare it with existing baselines, you can see, usually we need more than 20 to 40 steps to reason. And now we just need 2 to 4 steps to reason. And in terms of the speed up is like about 20 to 55 times faster than the previous baselines. And overall, the performance maintained the similar level with the original chain of thought model. So which means we maintained the reasoning accuracy while largely improved the inference efficiency and reduced a lot of hidden tokens. And another advantage is that, let's say, okay, you have different scenarios. Sometimes you're mostly doing fast reasoning, sometimes you're doing slow reasoning. You can control two parameters, which is one is for the threshold value to control the reasoning depth, and another is the number of steps for reasoning. And the good thing is, after you have trained such a model, you don't need to retrain the model. You just adjust these two parameters, like two buttons, and it will allow you to flexibly control. Shall my model have a higher bar to keep doing the reasoning, or shall I do reasoning for more steps, right? So in this case, you can configure your model with different configuration in different environments. To summarize, for this, what we call the system 1.5 reasoning, it dynamically allocate computational resources across both model layers and the decoding steps. So it's both vertical and horizontal directions, and it enables efficient latent space reasoning with controllable test time trade-off, and also achieved high accuracy with a lot of speed up, which is ideal for capable, scalable real-world deployment. So yeah, thank you. So this is the main content of today's talk.
Thank you very much, Professor Bang Liu. So now we'll have a Q&A period, and Pravin will be our mic runner. So if anyone has any questions, please raise your hand and the mic will come to you.
Thank you. Both very excellent talks. With regards to the first talk on memory, you concluded that implicit is better than explicit. Is that a given in all cases? And those RAG vectored databases is just an intermediary step, and RAG is not the final solution?
That's a very, very good question. So just some other audience asked me similar questions before. So here I'm not claiming that implicit memory is the best solution. It's more about the trade-off. So first, so what is the advantage of implicit memory? So let's say a memory of implicit is like a neural network. It continues to learn through the interaction with users, right? So basically, it knows about this user. In this case, when you just say some keywords, because the memory network knows about you, it can infer what is the semantic of this query. It can automatically complete the query into an understandable format and retrieve, or we can say generate the corresponding memory information. But a retriever is it doesn't know every user. It's just you give me this query, I'll try to come up with statistically optimal query expansion to retrieve the information. So this is the advantage of implicit memory to explicit. It's more personalized. It's continual learning. And we should combine both explicit memory and implicit memory. So in this case, you need to differentiate what are the long-term value information you should keep in the memory network. What are more details you can just put it in the outside and just retrieve it when you need it, right? These are something can be done by either external classification system or decided by the model itself during continual interaction. So that is the overview here.
Thank you for your question. We have time for one short question.
Hi. I'm not sure I totally understood the second talk that you gave. And I'm wondering if you could, so I'm not sure if I understand correctly, but one of the shortcuts that you are proposing is to skip layers in the transformer?
Yeah, so first, skip layers in the transformer is not a new idea proposed by us. So it's the paradigm of early exit. So because at different, let's say if you have 20 or even 100 layers transformer, but for some tokens, it's quite easy to predict, right? Because they are common sense language prediction. So maybe you just need 3 layers. You are easy to predict what is the next token. But for sometimes it's more complex. You need to understand more about the context. So in this case, maybe you need 100 layer or 20 layer. So in this case, you actually keep deciding at each layer, shall I stop to the next time step or shall I continue reasoning, right? So this is the early exit idea.
Okay, so once you get though to deeper layers,
yeah,
the vector of that token has transformed, like in layer 10 or whatever. It's different than in layer 3.
Yes.
And that is going to impact the other tokens in that layer. So you just keep it constant through the whole model?
I'll let you have one quick answer, and then we've got to wrap it up for the next speaker. 30
Yeah,
seconds.
I think for the details, I think you can check the early access paper or Coconut, which is a quite classical paper on latent reasoning. But the general idea is that if at this time step you are good enough to predict the token, for example, you can have a very lightweighted adapter to turn it into the final token distributions, right? So in this case, this can be kind of an early exit token predictor module.